Really, why do we have to even bother checking endpoints? So let's suppose that I want to find the maximum and minimum values of this function, f of x equals x minus x cubed. That function f, if I consider it on the whole real line, doesn't achieve a maximum or minimum value. F of x is really negative if x is really positive, and conversely, f of x is really positive if x is really negative. True enough, so let's ask a better question. What if I want to maximize and minimize this function on the closed interval from -3 to 3? This is now a continuous function on a closed bounded interval, so the extreme value theorem guarantees that I'll be successful, right? It guarantees that there is some input which minimizes this function's value and some input which maximizes this function's value on this interval. I'll begin by listing off the critical points for this function. So I'll differentiate this function, right? And if I differentiate that function, the derivative of x is 1, and the derivative of minus x cubed is minus 3x squared. All right, so there's the derivative. I'm looking for places where the derivative is equal to 0 or the derivative doesn't exist. Well, this function is differentiable everywhere, so there's no critical points where the derivative doesn't exist, but there are going to be some places where the derivative is equal to 0. Let's find them now. So I'm trying to solve this equation. I'll add 3x squared to both sides, really trying to solve the equation 1 equals 3x squared. Divide both sides by 3, so now I'm trying to solve the equation 1/3 equals x squared. Now I'll take a square root of both sides, and I'll find that x is equal to the square root of a third, or maybe negative the square root of the third. So I'll write x is plus or minus the square root of a third. These are the two critical points for this function. I'm also going to be careful to list the endpoints, and we'll see why we have to. So here are the points that I should check, right? I should check the critical points, and I just found those two critical points, negative square root of a third and positive square root of a third. And I also want to check the endpoints, right? And my original question is asking me to maximize and minimize this function on this interval, which includes the endpoint -3 and the endpoint 3. So I'm going to include those in the list of points to check. So where does this continuous function achieve its maximum value, and where does this continuous function achieve its minimum value on the given domain? So let's go ahead and just evaluate the function at those 4 points. Here are the endpoints, -3 and 3, and the critical points, plus or minus the square root of a third. And when I evaluate the function at these points, what do I find? Well, I find that the largest output occurs when x is -3, and the smallest, the most negative output, occurs when x is equal to 3. At these critical points, the output's, in size, no bigger than 1. It's about 0.38. What nightmarish scenario would have ensued had I forgotten to include the endpoints? Well, here's the danger, right? This is actually what I'm saying. I'm saying that if x is in this closed interval, then the largest value of the function occurs when x is equal to -3, and the smallest value occurs when x is equal to 3. If I hadn't included the endpoints in my chart, I would have been fooled into thinking that the largest output of this function was 0.38. But on this interval, on this closed interval between -3 and 3, the largest output actually occurs at this endpoint. The upshot to all this is that the endpoints are in some sense critical points. Standing at an endpoint, you can't wiggle freely, so you really can't differentiate when you're standing at an endpoint. And a place where you can't differentiate, well, that's one of the critical points.